So now we will discuss heterogeneous equilibrium. So heterogeneous equilibrium is when we're dealing with not just gas, but solid and liquid states as well. So it's really interesting because if you look at this, well, this was in our last experiment, right, where we have the sodium bicarbonate as a solid, and this is decomposing to sodium carbonate and CO2 and H2O. So in this particular equation, we see that there is a forward reaction and the arrow's moving to the right, and we see there's a reverse reaction with an arrow moving to the left. However, to have this be a reversible equilibrium reaction, right, for it to be dynamic, remember, you have to have a closed system. That is one of the criteria, okay? So if I go back, it doesn't matter, but you have to have a closed system. So how do we handle it when there's not just gases? Okay, how do we handle it when there's solids or liquids? So the concentration of the solids and liquids pretty much don't change. They remain constant. You can almost think of them as in terms of being the solvent, like in the aqueous phase, water would be the solvent. So their concentration is very large, typically, in proportion to the solutes, and the solutes being either the dissolved ions in the aqueous phase, or in this case, the gas particles. Solute being the lesser amount, solvent being the larger. But typically when you have solids and liquids, their concentrations don't change during the reactions that much in comparison to gases and aqueous dissolved dissociated ions. So with our equilibrium constants, our Kc expressions, now this says we're only writing compounds that are gases. We're also writing aqueous. Whoops, that looks really messy. Sorry about that. We're also doing it for the aqueous phase. And you'll see that in another section. But for right now, we'll just say gases. So how would we express this K of equilibrium if we're only doing it in terms of gases? So how do we write out a K of equilibrium? It's a ratio. Products over reactants. And I look at my products. So I have sodium carbonate, CO2, and water. But this is a heterogeneous equilibrium because the sodium carbonate is a solid. I'm only going to write the gases as products in the numerator. So I write my CO2 and my H2O. The reason why this quotient doesn't, I mean, it has a denominator of 1, but the reason why we don't see brackets or concentration for the quotient of products over reactants is the only reactant is in the solid phase. And we're taking into consideration that that concentration is constant and we're not incorporating it in the equilibrium expression. So your K of equilibrium is just equal to CO2 and water. And we'll see that this is really important in chapter 14 when we start talking about acids and bases and what is referred to as KW, water's equilibrium constant. So if that's the case, if we're only taking in consideration in heterogeneous equilibriums, can we still write out an expression of a K constant, a K of equilibrium constant? We can. So that's what this particular reaction is showing you. I have more than one phase here. I don't just have gas. Can I still write out this expression? So I'll give you guys a second to do that, and then we'll do it together. Okay, so as we said in the earlier part of the lecture, whenever they want you to write K, your equilibrium constant, just think products over reactants. That's the best way to think of this. So this quotient represents how these concentrations are proportional to each other. So what are my products? I look on the right side, I see potassium chloride and I see oxygen, okay? However, I'm only incorporating the gas because the solid is considered to be at a constant concentration, not really changing. So I just write O2 concentration in brackets. And then I look over for my reactants and I see that the potassium chlorate is in a solid state. So I don't need a numerator, or a denominator rather. I don't need a denominator in this quotient. So then the last thing I need to do is look at my balanced equation, look at my coefficients, and I see there's a 3 mole ratio for oxygen. So I use that as a power. I put that as a 3, and that would be my answer. What type of reaction is this, actually, other than equilibrium, which we know, of the 5 basic types that we've discussed?
Decomposition.
Yes, it's a decomposition. Good. And the only way we can have that double arrow is if we have this in a closed system. Otherwise, the oxygen gas would escape. So what else can we use the K of equilibrium for? Well, really, we can use it not just to express it as a ratio of proportionality of the concentration of products over reactants. We can actually, sometimes calculate for what that constant is. So if you're actually given the concentrations of your reactants and products at equilibrium, you can solve for the K of equilibrium. So how would you do that? Well, okay, K of equilibrium is products over reactants. And what would I do? Well, I would write out the concentrations. My concentration of HI, which is a product, and I see there's a 2, so I'm going to just put that 2 there before I forget it. And then my reactants, hydrogen and iodide, right? So I'm writing out my expression. Once I write out my expression, what do you think is the next thing you can do to solve for the value of K?
Just plug in the values.
Exactly. Plug and chug. That's what I call it. So how would we do that? Well, I would go, all right, my concentration for hydrogen iodide is 0.35, and whatever that value is, I'm going to square it, divided by the concentration of my hydrogen, 1.2, and the concentration of the iodine, 1.2, which kind of makes sense because it's a 1-to-1 mole ratio for that. And then I plug those values in the calculator, and I should get this value right here, 8.5 times 10 to the negative 2. So now I've actually calculated what that constant at equilibrium is. Now, one of the things you need to realize with equilibrium constant is it is actually dependent on temperature. So this constant would change at different temperatures. You're not expected to memorize any of these equilibrium constants. It's impossible. There are a set of standard constants at given temperatures, usually at 25 degrees Celsius are the standards. But again, you're never going to be expected to memorize an equilibrium constant. There's just too many of them. There's too many reactions. And those are typically determined experimentally anyways. So you're never going to be expected to memorize that. However, you might be expected to calculate a K of equilibrium just as we did here. So if you were given a reaction and the concentrations at equilibrium, you should be able to derive the equilibrium expression, or I call the equilibrium constant, the ratio, and then plug in the concentrations to get the actual value. So I'll let you guys work on this one and see how you do. Okay, so I'll give you a minute. You can work on that, and then we'll do it together. So did anybody get the value yet? Or you might still be working on it, so I'll give you a minute. But 0.26. Okay, that's correct. So how'd you do that, Sam? Well, what'd you do?
I just did products over reactants.
Okay, good. You like that. So I look at my products. I see carbon monoxide. It's a gas. So I'll just put brackets, carbon monoxide. I see hydrogen. It's a gas. And I see it as a coefficient of 3. And I said, make that an exponent. So that's cubed. And then I go over to my reactants. Methane, it's a gas. And water, in this case, is water vapor. So we're going to incorporate that in our equilibrium expression. And now I just plug in my answers or my values. So for carbon monoxide, 0.81 molar. For the hydrogen, it's 0.28. But don't forget to cube that. And then for the methane, I have the 0.13. And for the water, I have 0.53. And that should give me a value of 0.26. So again, you're not expected to memorize any of these, but you are expected to be able to write out the expression or the equilibrium constant, plug in the concentrations at equilibrium, and solve for that value. Now, how else is the equilibrium constant useful? Okay, so we're seeing that it's this expression of, proportions of products over reactants during a state of equilibrium where the forward and reverse reactions are equal. How else can it be useful? I mean, why are we calculating K? I mean, what's the big deal? Why would we even bother doing that? Well, the equilibrium can favor either the products or reactants. So in some reactions, the products will be favored. In other reactions, the reactants. And it's the K expression that will help us determine that. So we'll take a look. If we look at equilibrium of that reaction that we have right here of sulfur dioxide and oxygen combining to sulfur trioxide, if we initially have just reactants, we're going to get the forward reaction. And eventually, we'll get a certain amount of sulfur trioxide. Okay. And once we get a certain amount of sulfur trioxide, we can have the reverse reaction as well. Okay. If we initially only had sulfur trioxide, we would get the reverse reaction and we would produce the reactants. But eventually, in a closed system, I'm going to have all of them. I'm not going to only have one of these substances. I'm going to have all three. And that goes back to the collision theory that we first discussed in the first part of our lecture. What the collision theory is, once I produce product, now the product molecules, they're colliding and they're reaching the activation energy with effective collisions, and they're breaking bonds and forming new ones and going in the reverse direction. Okay. So at equilibrium, eventually this forward and reverse rate stabilizes. Okay. So if at first we only had sulfur trioxide, we would just see a bunch of reverse reaction until we eventually produced enough reactants where we would get the forward. And vice versa. If we initially started with just the reactants, we would have only the forward reaction until we built up the product and then get some of the reverse. But how can K tell us which one's favored? Well, if you think of it as products the concentration of products over reactants, it's quite easy. This quotient is representing a proportion of concentration of products over reactants. So if I have a really big number, like 10 to the 11, what does that mean? My numerator must be a lot bigger than my denominator, right? So for big numbers, right, products must be bigger than my reactants. So if my K of equilibrium expression is a big number, then that tells me, oh, in this particular equilibrium, I have more products at equilibrium than I do reactants. So a lot of times the way they denote that is the size of the arrow. So you see that the arrow in the forward reaction is much bigger than the arrow in the reverse. Why is that? Because we have much more of the products. And why do we know that we have more products? Is our quotient must be bigger for this number to be bigger. So when would equilibrium favor a reactant? So I can have, again, similar situation where I have an equilibrium, so a dynamic equilibrium, or initially I just have reactants, they move in the forward direction. As I build up products, they're able to go in the reverse. Or I can initially have a bunch of products, they go in the reverse direction. As I build up this, then part of the forward reaction takes place. But eventually, we're going to reach a state where the forward and reverse reaction rates are the same. It doesn't mean the concentrations are the same. So what helps us determine concentrations? Because we know at equilibrium, forward and reverse reaction occur at the same time. So how do we know the concentrations? What do we know about their relationship? Again, our equilibrium expression, our K of equilibrium. If the ratio is essentially a proportion of the quotient products over reactants, if I have a small number, now how do I know that's small? That's negative. That would be, you know, basically, oh my, I don't know why I decided to do this, but I would have 8 zeros in front. That's a really small number. That's not a very large number. So what does that mean? When K is small, right, the products aren't favored, the reactants are favored. There's more reactants. And that makes sense because the denominator must be big to get a really small number. So how do they depict this? Again, they use the arrow notation. You can see that the reverse reaction has the bigger arrow. And the reason why the reverse reaction has a bigger arrow, you have more reactants. A lot of times they refer to this as the major species. These are the major species at equilibrium. They're the major because I have more reactants than products. The product, which I have less of, would be considered the minor species. So those are terms you see in other textbooks, or you might hear somewhere else if you watch videos somewhere else. So that's how they refer to it. But again, essentially we're seeing, you know, the K, once we can calculate that K, now we know at equilibrium, even though the rates are the same, right? Where is there more? Are there more people in the club or are there more people in the line? Well, K tells us. And this is kind of what I'm showing. The one thing that we use as kind of we use this as a guide, as a scale, is if K is 1, that means your products over reactants, their concentrations are pretty much equal. That's why, you know, 3 over 3. So if I had a 3 molarity over 3 molarity, that would equal 1, right? So this, you know, to get 1, this concentration would have to be the same as this. These would have to be equal, and they would cancel out and go to 1. But if my numerator is much bigger than my denominator, then I get a large KC and add more products. If my denominator is a lot bigger than my numerator, well, that's because I have more reactants and I'll get a really small, right? So like, 1 over 10 to the 9 would give me a 10 to the negative 9. That's a small number. I have much more reactants. Just like a 1 over 10 to the 6. Well, I have 10 to the 6. That's a big number. I have more product. So you could easily now that you know how to calculate K of equilibrium constants using concentrations at equilibrium, you could, once you calculate the Ks, you could look at them and decide, okay, at this equilibrium, the major species is the reactant, or at this equilibrium, I have more of the product, simply by looking at the value of K. So when I look at this, is this number bigger than 1 or less than 1? Anybody? I know that's probably an obvious question. That's why no one wants to answer it. But is 1 times 10 to the 95 bigger or smaller than 1?
Bigger.
So this is much larger than 1. Right? If I go to 1.8 times 10 to the negative 7, that's a negative exponent, means it's less than. We talked about that way back when, week 1 with the metric system, when we were using that as a guide. So if my number is bigger than 1, that means the quotient is large, means I have more numerator, the products are favored. If my number is less than 1, it means I have a bigger denominator. And again, the quotient is products over reactants, right? So if this number is less than 1, I have a bigger denominator, means I have more reactants. And that's what this shows, right? So A is much bigger than 1, products are favored. B, right? It's much smaller than 1, so my reactants are favored. What if I'm actually given the equilibrium constant and I want to find a concentration? Is that possible? Like, could I, in this question, if this was a problem, right, and they want me to figure out the concentration of PCl5 at equilibrium in this dynamic equilibrium, how do I know that this is an equilibrium state? What indicates that this reaction's at equilibrium?
Reverse arrows.
Exactly, the double arrows, perfect. So as soon as you see the double arrows, boom, that's a state of equilibrium, okay? It's dynamic. Now, for me to figure out the concentration, the first thing I would need to do is set up my what? My K. Okay, well, what's the K? Products over reactants, PCl3 or NCl. So phosphorus, trichloride, chlorine, and then over reactants, phosphorus pentachloride. Now they want me to find phosphorus pentachloride. Well, how can I do this? Well, this is my K of, so they give me my K, give me the concentration of my products. So I can set up my expression. So how did they get PCl5 is 0.24? I didn't show all the work, so I'll do it here for you. I know my Kc, right, is 4.2 times 10 to the minus 2. So there's my Kc. And it's equal to what? The PCl3 and Cl2, so 0.10, and another 0.10, so I could just square that, right? And then on the bottom, I'm looking for phosphorus pentachloride, that's my X. So then I can just switch these two up and I get X equals 0.10 molar squared, because both of them are that, divided by 4.2 times 10 to the minus 2. And I would get that value. So can you do it for this one? Could you find the concentration at equilibrium for one of the substances in this equilibrium state if you're given the concentrations of the others and the K equilibrium constant?
I got 1.3.
Okay, sounds good. Thank you for volunteering, by the way. Appreciate that. So I think that was Jake. I'm not 100% sure, but I think it was. So was it you, Jake?
Yeah, it was.
Oh, great. So how did you set that up? What did you do?
I set up 2 equals 0.8 over 0.5.
Okay, so you set up your equilibrium constant, right? So you went squared, and what is this squared, Jake? Why is this squared?
Oh, never mind. I got the wrong answer. I didn't
Okay.
see the coefficients.
Yeah, you got to remember those coefficients. I'm glad you caught that. So that's okay. So what do I do now for nitrogen monoxide, guys? What do I have to put here? What does that 2 coefficient tell me?
To square it.
Yeah, it's a power of 2. And then I have my bromine, right? And then on the bottom, what do I have? NOBr, and that's squared. Okay. And then they give me, like you said, Kc, which is 2. So I'm going to just write this down here because there's more room. 2 equals, and do they give me NO? They do. 0.8, and that's squared, right? They do not give me the bromine, right? So I'm going to just call that X, right? They give me NOBr, 0.5 squared. Does everybody see what I'm doing?
Yes.
And then you can just solve for X. So how would you do that? X would just be 2.0 times, and what I'll do is multiply this by 0.50 squared, right, to get rid of that denominator, and 0.80 squared, and that should give me my answer. So did anybody get the answer?
0.78.
Yeah, I think that is it. So they leave it in this, they leave it, so they set everything up the way I did and set it up to 2, but the 0.78 for the X. I like to just plug in the X and solve for X. Kind of old school. That's how you get it. So before I move forward, because you know it's hard because I can't see your faces or hands. Does anyone have questions on if you were given equilibrium concentrations of some of the substances in a reaction, and you were given the equilibrium constant, would you be able to calculate concentration of one of the substances?